Hey guys, today we're going to take the flowchart that we've been using and take it to the next level, add the rest of it on. So as an introduction, stoichiometry really by definition is just looking at the branch of chemistry involving known ratios of products and reactants in order to figure out data that we don't know. So we basically use a known ratio with those product and reactants. And gosh, that sounds so familiar because it just seems like we've talked about that before. I can't remember it. I feel like we talked about a balanced equation as a ratio, because we sure did. Okay, so those of you that are like, oh god, I don't know how to balance equations anymore, I forgot, blah blah blah, fix it. But basically what we're going to be using in stoichiometry is using that balanced equation because that balanced equation is a ratio. That's our recipe. So in stoichiometry we're basically using these conversions and we are using it to make the recipe. Okay, so as a reminder, looking at the flow chart, sorry, I'm trying to fix this. Oh, it's only getting worse. Okay, well, whatever. That means moles. Okay. So looking at the flow chart, I wanted to remind you guys, of course, that when we're looking at this flow chart, we remember that what this means is that I can go either direction along this flow chart. Okay. And of course, I can go between these units as well. So I am able to actually convert between any of these things. When I look at mole, I'm referring to 1 mole, okay? When I'm looking at atoms or molecules, I'm looking at 6.02 times 10 to the 23rd atoms or molecules, okay? When I'm looking at volume, I'm looking at 22.4 liters, and mass is always going to be the molar mass in grams from the periodic table. Now, looking at a lot of the quizzes that we had today, many of you are for some reason grabbing these numbers and just kind of throwing them anywhere. And I want to remind you guys that if I see the word mole in a conversion factor, the only value I should ever write in front of it is 1. Okay. Now, in this lesson, I'm going to show you the only other exception where you might put something slightly different than 1, but you're only going to be putting 2 or maybe 3 or something like that. Okay. If we're looking at mass, you should only be calculating the molar mass from the periodic table. If I'm talking about atoms and molecules, I should only be putting in 6.02. Many of you get really excited about this number for some reason. That is the number of atoms or molecules within a mole. Okay, 1 mole is not 6.02 times 10 to the 23rd moles. Okay, some of you are deciding to say, oh, I have a mole, so I'm just going to write 6.02 times 10 to the 23rd. No, that's referring to how many actual particles there are in 1 mole, but that's different. Okay, if I say I have a dozen eggs, a dozen eggs is 1 dozen eggs. That may be 12 eggs, cool, but that's 1 dozen. So 1 mole is this many numbers, great, but that doesn't mean I have 6.02 times 10 to the 23rd moles. That would be a ridiculously large amount of matter, okay? And then anytime I have volume, I'm only going to be plugging in that 22.4. So be careful with some of those and make sure you don't make mistakes with those. Okay, so looking at a mole-to-mole problem, what we're talking about when we're referring to mole-to-mole problem is we're basically saying that we are now involving more than one substance. So we are now looking at 2 chemicals, okay? Well, I'll say 2 or more, okay? Because what we're now looking at is not just looking at a single substance, we're looking at an entire chemical reaction. And a lot of people find this to actually be easier than some of what we have been doing. Even though you're doing the same thing, it just kind of makes it a little bit more applicable. So hopefully, if you have been struggling with the molar conversions, this will help you as well, okay? So in this question, what we're going to do as we go through these questions or this particular practice problem is we're going to break it down step by step, so you'll get an opportunity to see as we go along exactly what every step is. So the question is saying, if you want to manufacture is this the right? Yeah, this is what I want. If you want to manufacture 150 moles, so I'm going to highlight that, okay, 150 moles of ammonia, okay, it says how many moles of hydrogen, so let me highlight that a slightly different color, will you need, okay? So First step, of course, is balancing our equation, but looking at the question, I know I'm going from moles to moles. I know I'm looking at a situation where I now have to use a mole-to-mole ratio, and that mole-to-mole ratio is going to be the balanced equation. So first step, balance your equation. That's pretty simple. Okay, so on this particular calculation, the second step is, of course, just what we have been doing. Identify what your given is and what your unknown are. Many of you are not doing this in your calculations and you're making mistakes. So go back to get into the habit of doing it. So in the first one, what we know is that we have 150 moles of ammonia. What we are looking for is moles of hydrogen. So I'm going to set up my conversion factor to get that in the bottom. And we can recall, of course, that this is the same as this. Okay, so if for some reason the format of it's throwing you off, it's the same. We have our train tracks, as many of you call them, to be the, oh, I made it worse. Oh, gosh. Okay. Anyways, we chose a conversion factor to put that units in the bottom. We know that's the case. Anytime we have a substance that we have out front and we want to get rid of it, we're just going to put that unit in the bottom. Next step is we're going to make sure that we ensure that we put the unit we want to get rid of on the bottom and the unit we want on the top. So we want to make sure that that is going to be what our unknown is. Obviously, we're looking for moles of hydrogen in this case, so there we go. The values we're going to get from that are going to come from the balanced equation. So by balancing the equation, in the equation I have that we have 3 hydrogens over here. Oops. 3 hydrogens over here. And then we have 2 ammonias. So what this is basically saying is that I'm going to need 3 hydrogens and 1 nitrogen to make 2 ammonias. Okay? That's what this is essentially saying when we're looking at this equation. And so I'm going to take those coefficients, that 3, and I'm going to plug it in right where it fits. And I'm going to take this coefficient of 2 and plug it in right where it fits, moles of NH3. So remember that the balanced equation is also called our molar ratio. That's what we're saying we need to put together. And when we say, oh, I need 3 hydrogens, remember that we can't just measure out 3 hydrogens. That's why we use the mole. So we're really saying we need 3 moles of hydrogen, 1 mole of nitrogen to make 2 moles of ammonia. When I perform that calculation, I'm going to take 150, multiply it by 3, divided by 2, and you should get 225 moles of hydrogen. So in this particular problem, it says we want to make 100 moles of ammonia. So we have 100 moles of ammonia, NH3. I'm going to go ahead and set up my conversion factor, put moles of NH3 in the bottom. Okay, it's asking for how many moles of nitrogen will I need. So 100 moles of ammonia is my given, okay, and then moles of nitrogen is my unknown. So looking at the problem, I'm looking at nitrogen right here, I'm looking at ammonia right there, all right. So in this problem, I put moles of ammonia in the bottom. I'm going to put what I want to go. Ooh, that ain't right. That is not right. That is not the right color. I want it to be this color. I'm going to put moles of nitrogen in the top, okay? And then all I'm going to do is literally find the coefficients and put them where they go. The coefficient in front of ammonia, boop, 2. The coefficient in front of nitrogen, boop, 1. 100 times 2 divided, or excuse me, times 1 divided by 2 is 50 moles of nitrogen, okay? This is a full and complete answer. It has a value, it has a unit, it has a substance. For this calculation, it's the same idea. Looking at the equation, I need 3 times as much hydrogen as I need nitrogen. So if I have 36 mole of nitrogen, multiply by 3, and that's how much hydrogen I have. There's a lot of logic in these. Make sure that your answers make sense. Now a reminder as you go through these gram-to-gram problems, look at that flow chart you have. Your flow chart shows you exactly what to do. These are not anything more complicated than what you have been doing. All you're doing is adding another conversion factor based on where you need to go. Okay. So a reminder, when we look at that, when we look at our flow chart, we see that over on the left-hand side, of course, we have our 3, and then we have moles. Okay. Moles. But if you look in the middle, it literally here says use the coefficients from the balanced equation to do a ratio between those two. And then I can go to mass, I can go to volume, and I can go to atoms or molecules, okay? And this would be of, let's say, substance B, okay? Whereas this side would be substance A, okay? So I'm going to use the exact same ratios that I used when I was doing single chemical conversions. It's just now I'm using my balanced equation to jump to the other side and then keep going. In a gram-to-gram problem, all you're going to do is start off the same, balance your equation, identify your given and your unknown, make sure that you're identifying them correctly. So my given in this problem, I'm looking at 100 grams of hydrofluoric acid, so I'm looking at this substance right here. It's asking how many grams of glass or silicon dioxide, so I'm looking at that substance right here. So all the colors should match up as you go through and highlight. Now in this conversion, this should look identical and very familiar to you. What we have here is we have grams of what we're starting with, 100 grams of hydrofluoric acid, and then a reminder that I'm going to need to put grams on the bottom because that is where I need to put that unit to get rid of it. I put the unit I want on top. I plug in the values from my conversion chart. Whenever I see moles, I plug in 1. Whenever I see molar or grams, I plug in the molar mass. So hydrogen plus fluorine makes 20.08. Now that I'm in moles of that substance, what I can do is convert to the other substance, okay? So by getting into moles of one substance, it allows me to convert into moles of another substance. So I then take moles of hydrofluoric acid, I put it in the bottom of the next conversion, I put what I want on top here. Of course, that means that these are going to cancel, and I'll be left with moles of silicon dioxide. That's not what my final answer needs to be, and I want it in grams of silicon dioxide. But I take those coefficients, the 4, plug it in right there. I take the 1 from silicon dioxide, plug it in right there, and then I keep going. A reminder that I know that I'm done when I finally get to a point where the unit I want is the unit on top, okay? This is a little wonky because of the formatting and everything, but I'm setting it up with our train tracks so you know. The unit I wanted my answer in is in grams of silicon dioxide. So once I get it to a point where everything has canceled except for that, boop, boop, ching, then I am where I want to be. This needs a 2. I think it was there. It just got cut off. But once I get to that point, I'm done, okay? And this is why we started with individual conversion factors, because if you look, looking at this, I can see here, that's a mole to mole, okay? But everything else is stuff we've already done. We know that the molar mass should be equal to 1 mole. So we can use those known factors to get to the answer that we want. So I did a quick setup on this because you guys are showing that you're pretty good at doing molar mass, so I wasn't going to show you how to do that again. Your molar mass, of course, for water would be 18.016. Silicon dioxide, you add up silicon and 2 oxygens, plug those in. And then what I'm going to do as I actually put this into my calculator is just like we've been doing. Take 230 times 1 times that value divided by that, divided by that, divided by that. Oh. Divided by that, which is 1. Okay? So when I go to put that into my calculator, that's how I'm going to kind of flow it through. Now, look at your flow chart, and what you'll see is that we've been doing gram to gram. Okay, so we're going mass down to mole, across to mole, up to a mass. But we can do any calculation. I could do molecules to moles, to moles to mass. I could do volume to moles to molecules, or whatever I want to do, I can flow across that chart. So for our final slide, I just wanted to show you one of those particular calculations that I was just talking about, where we're not going from grams to grams, but instead going from grams to liters. Or excuse me, from liters to grams. So I'm going to start 27.2 liters of CO2, okay? And then I'm just going to go, this is a long one, so we're going to get it ready. I'm going to put liters of CO2 in the bottom, okay? And then I can go to moles of CO2. And then I can go to, using moles of CO2, I can convert to moles of, I'm not going to write the whole thing, so I'm just going to put GLU for glucose. Then I can put moles of glucose in the bottom and ultimately end up with grams of glucose. Okay, so notice how I do my units first. That is important. Many of you who are making mistakes are not putting your units in the right place, and you're not putting your units at all, and that's why you're making mistakes, okay? So what I now want to look at is, I want to look at just what I see here, okay? So I see this is a conversion factor, okay? This is a conversion factor. And this is a conversion factor, okay? And so what I'm going to do is essentially plug in as I go along. But I want to make sure that as I plug in, I'm plugging in things that are true, okay? If what is in here is not true, then you did it wrong, okay? So when I look at this, I can look on my flowchart and I see that 22.4 liters of anything is 1 mole of that substance. That is a fact, okay? As long as it's a fact, I did it right. Looking over on this side, glucose through CO2, I want to use my balanced equation coefficients because that's a mole to mole. So once I balance this equation, it should end up being 6, 6, and 6. I know it's a little demonic, but oh well. So I have 6 moles of CO2, 1 mole of glucose. Okay, that's from my balanced equation. And then over here, again, this needs to be a fact. So 1 mole of that substance needs to equal the molar mass of that substance, which I don't remember right now. Well, it'd be 6 carbons, 12 hydrogens, and 6 oxygens, okay? Once I plug in that right here, I should be able to multiply all the way across the numerator, divide all the way across the denominator, and get that, okay? So we're going to be using a lab next time to kind of show how to do these a little bit more, but what I've color-coded here in blue and yellow, you have already been doing, and you should have already been doing correctly. If you are still struggling with what's in the blue and the yellow, I have posted a couple of videos on the website. Please go watch them. Do not come in and just say, I don't get it, I don't know what I'm doing, because I'm going to ask you all those questions. Did you ask me questions? Did you do this? Did you do that? So make sure, please, that you spend the time to be sure that what's in yellow and blue you are good with. The green is the new section. That's just coming from the balanced equation, so it's usually one of the easier things for people to understand. All right? Bring in your questions and try to run through some of your practice. I'll be posting a key for it as well, and I will see you tomorrow.